Welcome back to Chapter 2 of the Spring Framework course. The fundamental principle in Spring is called Dependency Injection, and in this chapter we'll be focusing on what that is and why it can help you build better software systems. We'll begin by looking at a problem that can affect your software architecture, and that's called coupling. Coupling is a bit scary in that you often allow it to creep into your system without realizing it. In this chapter, I'm going to use a really simple example to illustrate what coupling is. We will be working on much bigger examples in the rest of the course. Dependency injection, which is the most important concept in Spring, is designed to help with the problem of coupling. You might be surprised at how simple this really is. Most of it is just basic Java. At the end of the chapter, we'll meet the concept of a container. Using a container alongside dependency injection is a good solution to the problem of coupling. There won't be any Spring in this chapter. Instead, we're studying the concepts. But we'll see that Spring gives us one of these containers, and that will set us up to use Spring for the first time in the next chapter. We're going to begin with a very simple scenario. This is just going to be a small example to help me to explain about coupling and dependency injection. We're not going to be coding this application for the rest of the course, so there's no need to follow along yet. You can sit back and relax for a bit. We have an application which is going to be managing invoices for a company. And the initial design, which I've sketched up here, is just 3 classes. We're starting with the client class, which for now will be just a standalone Java console application. Eventually, we'd probably make this into some kind of a web page, but for now, a text-based console application will do. We then, in the middle, have a service class. This is where the application methods will appear. By application methods, I mean the methods that the clients want to call. The application is going to be storing data in a relational database. Following the normal Java or the normal software design pattern, we're using a DAO to hold the data access code. A DAO, or a DAO as it's sometimes called, is a data access object. The aim of this is to make sure that all of our database logic is stored in a single place. Let's say, for example, that the save method here is going to be using JDBC to persist the data. Now, by the way, I don't know if you're familiar with JDBC. That's quite a basic library that we can use to access relational databases from Java code. It's built into the Java library, which is good, but it is a bit of a pain to program. A simple design then. What we're going to do first is look at a naive way of implementing it. An obvious way of implementing it, but one which will cause some problems. We'll then have a look in detail at what those problems are and how we could do it better. Now, because I'm just using Eclipse to show a concept here, you don't have to code along with me right now. But of course you can if you want, so if you are following along with me, the easiest way is to fire up Eclipse, and when it asks for a workspace, the workspace you're looking for is the workspace for coupling that you will find in the Practicals and Code folder for this course. Make sure you select the workspace and not the project. At first, you'll see just an empty workspace. Well, I'll close the Help tab first. Then you can go to File, select New, and then Java Project. On the dialog box here, type in the exact name of the project folder that's inside the workspace, and that happens to be coupling example. And be careful to include a capital C and a capital E. And if you get this right, you'll see this text here indicates that the source for the project already exists. Now, if you don't see this message, check your spelling up here. If all is well, you can now click Finish. And you should now find source code in the Package Explorer. Now, when we start writing Spring code together, we'll usually be writing code from scratch here in Eclipse. But as in this chapter, I'm just explaining a concept, I've already written some code before I started recording. We'll begin by looking at the domain class that we're working with in this application, which was the invoice class. I'll just close the task list and the outline. Now, this is our invoice class, and it's supposed to represent an invoice for a customer. For the purposes of this simple exercise, I've made this class very simple indeed. We have here just a few attributes, an invoice ID and a customer name. I also have a constructor, a simple toString implementation, and a couple of get methods. I'll be needing those in a few moments. It's a very, very simple domain class. Now, of course, in a real application, this would be much more involved, and there would be quite a lot of business logic in there. Now let's switch across to the DAO. This is invoicing DAO. For the purposes of this exercise, the implementation of this class really doesn't matter. But what I did a few moments ago was I threw together a very simple, quick and dirty implementation of a JDBC data access object. I'm just loading the driver here in the constructor, and then in this save method down here, I take in an instance of an invoice and then use the very ugly JDBC API to save that row into a database. Now, please don't send in any messages complaining about our implementation of this DAO. It's certainly not clean, it's certainly not perfect, but it should work. Now, in this application, I've decided to use a database called HSQLDB. You'll find a jar file for that in the lib directory. And the reason I've used HSQLDB is that it can create a database on the fly in memory, and then at the end of the program, the database is written to a file. You can run HSQLDB as a traditional server-based database, which is fine, but I like the idea of an in-memory database for the course, because that means that you don't have to worry about installing a database, configuring it, and all the rest of it. If you want to use a database like Oracle or MySQL, you just go in here and change the driver and the URL of the database, and everything else should still work. Feel free to do that if you really want to do that, but I won't be able to give you any support on that. The beauty of this workspace is that everything should run without needing any external dependencies. So that's the DAO and the invoice. Now let's look at the rest of the code. If you recall from the design said that the clients are not going to call the DAO directly. Now that's good design. We wouldn't want the clients to be coupled directly to the data access objects, because if we wanted to change the data access strategy later on, maybe we might want to use Hibernate in the future, then we'd have to go and change all of the clients. It's good practice to have an intermediate object, and that's what we're calling the service object right here. As you can see, the implementation of the raiseinvoice method is very simple indeed. We're just creating a new instance of the DAO, and then we're calling save. However, Going forward with this design, we may introduce some kind of logic into this class, but this will do for now. Finally, we have the client side of the application, which, yep, again, very simple indeed. I create a new instance of the invoice service. Step 2, I'm just creating a test invoice here with the attributes 11075 for the invoice ID and some customer name for the second attribute. And then I'm passing that on to the service object. We have what looks on the face of it a fairly simple, workable architecture. Does it run? Well, we need to check that. So I'm going to run the application, right-click on the client, Run As, and Java Application. Now, on some versions of Eclipse, there's a bit of a bug, and it seems to have affected my version of Eclipse. I did run the application then, but nothing seems to have happened. But if I go to the Window, Show View, and I'm looking for Console, this line here is telling me that actually the program did run, and it terminated without any errors. Now, I want to check the database. As I mentioned, we're using HSQLDB here, which runs in memory. There's no need to run any separate database. And what it will do at the end of a successful run is it will write all of the data into a file, and that file will be picked up on subsequent runs. To see the database, click on the project and either click F5 or right-click and select Refresh. And you can see here that 2 new files have been created. The properties file isn't very interesting. You can look at it if you want, but there's nothing of great use in there. But inside the script file, well, actually, this is opening up in Notepad. If I want it to open up in Eclipse, I'll need to select Open With, and I think it's Text Editor. Yeah, it's now opening up in Eclipse. And you can see here there is an insert statement with exactly the data that we've just inserted from our previous run. Now what happens is when we run this program again, HSQLDB will parse this script and it will use this to regenerate the database. So it certainly looks like the program ran and we successfully got data into our database. Okay, but I can think of 2 serious problems with this naive way of working. When we've got a really small program, it might not be obvious that there's something wrong. But of course, over time, this application is going to get bigger with many more classes added. And I'm afraid that if we continue working like this, we're soon going to start hitting some problems. The first problem is that if our application continues to grow, then changes are going to be difficult to make. Let's consider our DAO. Now, I deliberately said that this DAO is not a particularly good DAO. There's a lot of hard coding inside here, the SQL statements, the driver name, and so on. Now, this is a really poor strategy for acquiring database connections. In a true Java application, we'd want to use a more sophisticated way of handling database connections, such as a connection pool. Now, if you don't know what one of those is, don't worry, because we're going to be talking about that in detail later in the course. But the point is, I'm almost certain to need to change the code in this class. In fact, it's more than that. I probably would want to get rid of the entire class and start again from scratch. Let's say we decide to use a better database strategy, to use maybe Hibernate later in the future. Now in that case, rather than going into this class and changing things, we might decide to write a brand new DAO called Hibernate DAO. Now, I'm just going to do this for illustration. You don't need to follow along with this part of the course. So I'm going to call this Hibernate DAO. Now, although this class is going to be implemented differently, it will have the same method as our previous DAO, which is going to be the method called save, taking in an invoice, which I'm calling new invoice. Now, I'm just going to put a stub implementation in here, just because for now the implementation isn't important, but I'll just put in there saving an invoice using Hibernate. In real life, there would be lots of Hibernate code appearing here. So we now have a brand new way of saving invoices. Now, the huge problem is that in order to make this change become part of the system, I now have to go across to the invoice service class, and I need to make changes. Now, the changes I would need to make, I would need to change the class name here to Hibernate DAO, and I would have to change the class name here as well to Hibernate DAO. And now I would have to recompile and test my changes. Now, of course, this looks very simple here, but that's because we've only just started with this application. Consider that change in a full-blown application where we might well be calling the DAO from dozens or possibly even hundreds of classes, certainly hundreds of methods. This would be a really painful change to make. And the reason that this change is painful is because we've hard-coded the specific implementation classes here into the code. Now, for large-scale projects, this is not desirable. The next problem with this architecture is that it's likely to be difficult to unit test any of our service classes. With unit tests, we need to be able to test in isolation one object at a time. So in the case of the invoice service, all I want to do is test this one class and have no dependencies on the external environment. Now, at the moment, there isn't any interesting logic in this service class, so really, there's nothing to test. But I'd just like you to imagine that possibly after calling this save method, we might apply some logic to the invoice. And I don't know, it could be something like if the invoice is in an invalid state, a not valid state, after it's been saved, then we might throw an exception back to the client. Now that is definite logic, and I would want to be able to test that that works correctly. Now, I'm assuming that you're reasonably familiar already with the concept of unit testing. If not, we do cover it in our Java Fundamentals course, but I'll go very quickly through the basics of the kind of thing you might do. We would create a new class specifically for testing, and this is built into Eclipse. We can select JUnit test case. I'm going to go for a JUnit 4 test, and it's automatically called the class invoice service test. I'll just click finish there. And because this is the first time I've created a JUnit test, it's asking me if I want to add JUnit to the build path. I do, so I will click OK. Now, in a real project, we'd definitely have these tests in a separate package, but for this example, it should be OK. And we write a test method for every piece of interesting functionality in the object we're trying to test. So, for example, I might be doing something like test that sending an invalid invoice will throw an exception. You do tend to have quite long names for these tests. And the general idea inside each test method is we would create a new instance of the class that we're trying to test. So in this case, it's the service. If I can spell invoice service correctly. And then I need to create some test data. So I'm going to create an invoice. And this is going to be deliberately an invalid invoice. Now, because we're not really writing this system, I don't know what makes an invalid invoice. But let's say, for example, that an invoice ID should be a number, but in this case, we've added a letter to the end of the invoice ID. I think we also need to supply a name in the constructor there. So what should happen now is if I call the services raise invoice method, passing in this invalid invoice, we should get an exception. And I won't go into details on how to do this, but we could test here that an exception is thrown. Now, this doesn't really work as a unit test at all. And it doesn't work because by running the test, we will be unavoidably accessing the environment. In this case, we will be writing data to the database. Let me illustrate that by, if I just go back into my invoice service, at the moment I'm using this Hibernate DAO, but I'm going to change it back to our original invoicing DAO, which you'll remember really does write to the database. Now, if I run this test, and I can do that just by right-clicking and run as JUnit test. Now, the test has run. Now, it is passing just because we're not doing anything that might fail at the minute, but the test ran. But the problem is, of course, if we look at the database script now, we've written some data. There's Jack Jones written into the database. Now, consider that this could be a production database, and we've just now polluted the database with test data. And the other thing is, tests, of course, tend to run often. Every time I make a minor change to the application, I'm likely to want to run the test again. So I'll just simulate that by running the test a few times, which we'd certainly expect to happen while we're developing. And I think you can guess what's happened now if we go across to the database and look in the script again. I really have polluted the database with lots of test data. This is not good at all. Now, I could go back to the code, back to the test, and I could in the test do something like go to the database and delete the rows that I've put in when the test is finished. But that would get really messy and would still be dangerous, especially if we're working with a production database. I know a more subtle problem with this is that unit tests need to run as fast as possible. Because we're going to be running them often, because our unit test is now writing to a database, this unit test is going to run really slowly. Well, okay, it maybe doesn't look that slow right now. I don't know if you think that was fast or not, but with a few more tests in place, we're going to start to feel the overhead of these unnecessary trips to the database. And it is quite a common complaint on real-world projects that, oh, we've stopped running our unit tests because they take like an hour to run. And often the reason that that's happened is because their unit tests aren't really unit tests. They've started accessing external resources like files and databases, so they're naturally running slowly. So I've talked there about two problems with the architecture, but really the two problems are the same problem, the same fundamental problem, and this fundamental problem is coupling. Now, coupling is when two classes are dependent upon each other. And put simply, if you need to change one class, then you might need to change the other class. Now, we need coupling in any application. Otherwise, all of your classes would be disconnected from all of the other classes. And without talking to each other, the classes aren't going to be very effective. We need some coupling. But the trick is to reduce coupling as much as possible. It's unnecessary coupling that's a bad thing. Why? Well, systems with a lot of coupling tend to be brittle. Changes tend to ripple across the design, and I think we've all been there. You know, when you change one class and you end up having to change lots of other classes that you didn't think you should have affected. Now, as we've seen, coupled systems get hard to test. Because when you're testing, one thing you really want to do is to be able to look at one single class in isolation. If the classes are coupled together, then it's very difficult to tease them apart. Now, it's important to mention that coupling can't be eradicated completely. We do need some degree of coupling in any system. For example, the following code, perfectly normal, straightforward Java. But there's coupling here. Here, we've coupled our code to the Java string class. Now, as you know, of course, this is part of the Java library, and this class is outside of our control. Now, this is coupling because if the string class were ever modified, let's say someone in charge of Java removes one of the methods from the string class, then our code might break. However, do you care? Now, probably not. We can almost always accept this. The string class is unlikely to vary. The Java people at Oracle would never dare mess around with the string class. But in any way, we generally accept that the string class is what we need here. Some classes just live together and they're coupled together by their very nature. For example, in this domain model, we might have a customer class and an order class. Now, as we know, customers raise orders. It's a natural, real-world relationship. So therefore, I think it's only natural that these classes should be coupled together in the code. And as you can see here, the customer class is creating new instances of the order class on the line I'm highlighting here. And I think that's absolutely fine. It is coupling, but we accept it. Now, what we're really interested in for this course is what I'm going to call the architectural coupling. That's the coupling between the tiers of our application, such as for, in our example, the service tier and the DAO tier. It's almost always desirable to decouple here, because we probably want to be able to change things around. We want to change one tier without affecting the other tiers. Now, in our example system, we've already identified that there are at least two reasons why this DAO class, this dependent class, might need to change. Just to remind you, first of all, we might want to change the strategy that this DAO object uses to access the database. Secondly, we might need to test the service class without the DAO being present. But we can't make these changes because we've coupled the two classes together hard. The line of code here, with the new keyword, is almost like we're taking these two classes and we're fusing them together. We need more flexibility here. So how can we reduce coupling? Well, there are 3 steps we can apply. And over the next few moments, we're going to look at each step in turn. Now, I should stress that each of the 3 steps on their own is not enough. We're going to need to do all 3 steps together. Step 1 is going to be, we're going to program to interfaces. Step 2 is going to be dependency injection. And step 3, and this is where Spring is going to help, is to centralize the configuration of our application. Now let's have a look at each of these 3 steps in turn. Step 1 then is programming to an interface. Now this is actually just standard Java, so I will assume you know most of this already, and we do cover this in our Java Fundamentals course. An interface in Java allows us to define just the specifications of the class without providing an implementation. It's almost like making a design of the class, but putting that design into the Java. For example, Here I've written an interface describing what I would like an invoice data access object to look like. I'd like it to have a method called save, a method called delete, and a method called update. Then, what I would typically do is to create implementations, one or more of them, of this interface, and I can create as many as I like. Then, by referring to just the interface wherever possible through the code, we can then switch the implementations around at runtime to suit our needs. So let's have a look in Eclipse. Here I've created my interface, and I did this off camera so you wouldn't get bored watching me typing. If you're following along, then you can do the same, or you can find it from the complete version of this project in the Practicals and Code folder. It's exactly the same as you saw on the screenshot before. The key thing is now when I come to implement the data access objects, for instance my JDBC version here. Oh, and by the way, I've also off camera renamed this class to make it more meaningful. I'm saying that this is the JDBC implementation of the invoicing DAO. If you need to do that, you can right click on any class, select refactor and rename. And what I would do now is use the implements keyword to tell Java that this is implementing the invoicing DAO interface. Now, although I haven't mentioned it before, if I go down in this class, you'll see that there are implementations of the delete and update methods, although they don't do anything useful just yet. Now, if we go across to our Hibernate DAO, remember this is the alternative implementation that we have of a data access object. I would do exactly the same thing here, in that this is also going to implement the invoicing DAO interface. Now, at the moment, I have an error in my code here, and that's because I haven't included the delete method and the update method. And the great thing is I can use Eclipse to automatically fix this problem. I've just hovered over the red line there, and it's giving me a quick fix of adding the unimplemented methods, and it automatically fills in the implementations. Now, just for the purposes of this demonstration, I'm going to leave these two methods as stubs with nothing in them, but the key point is I was forced to implement them by Java. Now, switching across to the invoice service where we're actually using the DAO, notice at the moment I'm hard coding the specific concrete class name that I want to use. Now we know now that's coupling and it's not good. So instead, I'm going to follow the principle of programming to an interface. And all that means is I'm going to refer where possible to the interface rather than the implementation. I can do that here on the left-hand side by making that now be just a reference to the invoicing DAO, and notice the code still compiles. Now this is our first loosening of the coupling. I'm trying to say here that I don't care about the specific implementation class that's being used. That's not enough on its own. Notice we are still referring to the concrete class name here. At some point we have to create the objects. Have a look there at the new keyword. Now the new keyword is always a sign of coupling. Without recompiling this code, there would be no way of changing that implementing class. So that means we still have coupling here. So step 1 was necessary, but it's only one step. This is going to lead us to step 2, which is called dependency injection. Dependency injection is nothing more than a fancy term that means to pass in the collaborating objects as parameters rather than hard coding them. Although dependency injection sounds like a really big, and fancy term, it's actually really simple Java. Let's switch across to Eclipse and see how it works. So back to our service. Now, one thing that's odd in here at the moment is that if we had more than one method, and of course we probably will, let's say there was also in here a void method called updateInvoice. And maybe this takes an updated invoice. Now we would need a DAO in here as well. So we could copy and paste the code here, add it to here, and then maybe go ahead and call the method on the DAO. But that's just repetition. So what I'll do to tidy this code up is to make the DAO become an attribute of the class, because it's silly really creating this DAO twice. So I'll make it an attribute, the type being invoice DAO, that's programming to an interface again. And I'll call the attribute DAO, and sorry, that's called invoicing DAO. And then I don't need this line of code here or here. So that's a bit tidier. Now, of course, I'm going to have to create the invoicing DAO object. So I could instantiate it here. And as before, we'd have to choose which implementation we want to work with. So I'm going to go for the JDBC version here. Remember, though, that it's this new keyword here that's the statement of concern. This is where the coupling comes in. Now, all I'm suggesting with dependency injection is that we're going to stop creating the object, the DAO, in this class. I'll remove that. And instead, we're going to provide a method, a public void method, which by convention we're going to call set, followed by the name of the, well, I suppose this is now a property, if you like, that we're trying to configure. So for us, it's the DAO that we're trying to set. And the method will have a single parameter, and we're going to insist that we pass in an instance of the invoicing DAO. And I think I happen to have used a capital A and a capital O on that class name. That's now right. Now, the implementation of a set method is usually just a trivial save the object. So here I would say the attribute called DAO will be set to whichever value has been passed in. Now, this simple change that we've just made here is called dependency injection. Rather than creating the object directly inside here, we're going to allow it to be created externally. It might not look like a big improvement, but we've now got a lot more flexibility, as we can now use this class in more than one way. We could instantiate the service and pass in a JDBC DAO, or we could pass it a Hibernate DAO, or we could pass it a testing DAO. We haven't seen a testing DAO yet, but we could write one. So a small change, but we've added just that little bit more flexibility in the connection between this class and the DAO. Let's go back to the client. Now remember, what we're doing in the client is we're creating the invoice service, and then we're passing in an invoice for it to save in the database. Because we've now decoupled the service and the DAO, we can, in here, in the client, create an instance of the DAO. So I'm going to create invoicing DAO instance, which I'll call DAO, and we'll instantiate this as an invoicing DAO JDBC implementation. And I could have chosen the Hibernate version if I'd preferred. And now we can tie the two together by calling invoices dot set DAO, passing in our DAO objects. So we now have the freedom and flexibility to change this DAO around. It's all compiling and it should run fine. Let's test this. And if we look in the database, yeah, we've now got a new instance of this 11075 at the bottom of the list. I could double check that by changing this ID to 11080. And yeah, if we check in the script, there it is at the bottom. Now, if at a later date we decide that we don't want this JDBC implementation anymore, let's say we want to use the Hibernate version, it's a minor change here to switch the implementation around. Let's try that. And my naming is a bit inconsistent. I think I called this one Hibernate DAO. It's compiling, and because we've only referred to interfaces inside this set method, it's fine to pass this in as an instance. Now if I run the code, as you can see, we're now using the Hibernate version, and I didn't have to go into the service and make any changes in there. Now I think we've gained some flexibility, but I hope at this point you're feeling quite uncomfortable, because this way of working isn't very pleasant either, because every time I want to use this service class now, I have to manually pass in all of its dependent objects. It's really made using this service class a real burden. And of course, if we forget to do this dependency injection, let's say we forgot to do this set DAO, maybe we've even forgotten to create the DAO. The client is now really as it was before. You can guess what will happen if I run the client now. We get a null pointer exception because this invoice service has not been correctly configured. So if I just undo that change, this kind of assembling the service object every time we use it would not be viable in a real system. So this is where step 3 comes in, and this is where the whole process comes together. And by the way, this is where Spring is going to help as well. The dependencies between our architectural objects, such as our services and our DAOs, could be captured all in one single place. We're going to centralize this configuration. Now, this is good software practice. If something is likely to vary, we should encapsulate it and hold that thing all in one place. Then when changes do need to be made, we know that we only need to make the changes in one place. Now we're going to capture these dependencies all in a single place. Now what we could do is we could write a special class whose responsibility is to configure, or rather to create and configure the objects that we need. Now you could almost think of this class as being almost like a system configurator. Now, that's not a term that's used in the industry as far as I know. The industry calls this class a container. Now, writing a container isn't very difficult. What I've done here is I've written a very crude and very basic implementation of a container. Now, as I've mentioned here in the comment, don't worry, we will be using a real one in the next chapter, and you'll see that real ones are very much more sophisticated than this, but I hope this will at least get the idea across. So what I did off camera was, and again, I've just saved you the tedium of having to watch me type this in, but you will find this class in Practicals and Code. And what I've got here is a method inside this class, and I've made it a static method so it's easy to call. And the method's called getInvoiceService, and it's going to return an instance of the invoice service. Now what it's doing inside here is it's creating all of the objects for us that the service depends upon. Well, in our case, it's only one dependency, this DAO, but in real life, there could be more dependencies. So it's creating the DAO, it's creating the service, and perhaps most interestingly, it's connecting the two objects together. And the beauty of this now is if I go back to my client, instead of the client creating the invoice service directly, what we will do instead is we will ask the container to do the work for us. So I can just say crude container dot get invoice service, and then with just this single line, the client will have a fully instantiated and ready to use invoice service. And my client code doesn't now have to bother creating the DAO and connecting them together. So I can remove these two lines. Let's just check that that works. Now I think we have some big wins here. The client is relatively small and clean. The client doesn't want to worry about how to construct an invoice service, so it just asks the container to do the job instead. And then the client gets on with its work. And our invoice service is clean as well, because it doesn't refer specifically to any particular implementation of that DAO. So we've got the flexibility here. Now the trouble is this container is a very crude container. Now let's say that our project leader decides that we're not going to use JDBC anymore. We want to switch to Hibernate instead. Now we've already written the Hibernate DAOs, and we've got a big win really in that we know that to make that change, we'll find all of the references to the DAO implementation in this single container class. Now you can imagine this container class will be pretty big on a real project. It's quite small for us, but at least all the references would be in one place. So I would just find this JDBC reference here, change it to the Hibernate DAO. That one change in this one class now means if I run the application, it's now using Hibernate instead. But let's be honest, it's still not great because I've got to find this class. This class, by the way, would get really big on a real project. And I've still got to change Java and I've still got to recompile. A much better container would, rather than working from hard-coded dependencies here in the Java, would read from a file instead. And it would be great if we could somehow put in that file the dependencies that we have. Then we'd be able to switch from JDBC to Hibernate by just changing that config file. We really would have complete freedom and flexibility to change our architectural tiers around. However, writing a sophisticated container that's going to be able to read configuration files and parse them and presumably do error checking and things like that sounds like very tedious and time-consuming work. It would probably take months to implement a sophisticated container. Luckily, in the past few years, some open source projects have already implemented dependency injection containers for us. Now, one project called Pico Container, at the address you can see here, have implemented exactly that, a container that honors the dependency injection pattern. In other words, the software that you can download here would provide a really sophisticated implementation for step 3 of our plan. Now, as you can see here, this project has been running since 2003. In the first edition of this Spring Framework course, which we recorded back in 2008, we mentioned that Pico Container was a leading container. I must say, though, that by the time of this recording in 2013, Pico Container seems to be not used so much these days. But it's a good example of how you can get pre-written containers to really make step 3 much easier to work with. Now, back on that first edition of our spring course, Google had decided that they like dependency injection as well, so they got in the act and they began a project called Google Juice, which they describe as a lightweight dependency injection framework. And this is a very similar idea. When you download Google Juice, you effectively get a pre-written container. You'll find this at code.google.com. And as of this recording in 2013, Juice has been really successful. You're going to find it's used on a lot of projects. Now, there are some other implementations of containers out there as well, but of course, this is a Spring course. And the point of this chapter is that Spring features at its core a dependency injection container. Now here I am at the Spring website. We'll be using this website a lot through this course. And if we just have a look at their introduction here, you'll see really their number one feature is dependency injection. And to make that work, they provide you with a very sophisticated, fully operational container. And we're going to be using that container in the next chapter. And through subsequent chapters, we'll be going further with the Spring framework, and we'll be seeing that this container provides additional features such as transaction management, security, database access, and so on. And the point of this course is to show you how all of this works. So I hope that was all okay. I've tried to make the example as simple as possible, really to show that the problem of coupling might not be immediately obvious. But as your system gets bigger and bigger, coupling really can leave you in the state where your application is brittle, the layers are difficult to change, and difficult to test. Dependency injection is just basic Java, and you might be surprised at how simple it is. It really is just a case of providing a setter method to allow dependencies to be injected. But you will need a container. If you don't want to write one yourself, then you need to get one, and Spring features one of these containers. So in the next chapter, we'll be using Spring for the first time, and we'll be concentrating on how to use that container. So I'll see you in chapter 3.